Hi folks! Today we're going to take a look at an activity that my students and I designed for a lesson on atomic bonding. This hands-on activity introduces my middle school students to the concept of bonding between atoms of metals and nonmetals, and the formation of various molecules and compounds. The goal of this activity is to emphasize that some atoms can form bonds and some cannot. Hydrogen, for example, can form 1, while carbon can form 4. And the noble gases can't form any. If you'd like to 3D print these files, the links are provided in the description. So let's get started. I started by having my students design their atoms in Tinkercad. Each design followed specific dimensions, and students added 3 lines of text: the element name, the symbol, and whether it's a metal or a nonmetal. It was then time to print the atoms. I chose to use the same cliched colors that have been used for atomic models for decades. I wanted to have a healthy mix of metals and nonmetals, focusing on elements that are key components of important molecules and ones that are familiar to students. To represent bonding behavior, metals were given a semicircle cutout and nonmetals a square. Next, we printed bonding chips to represent the 2 types of bonds students would be working with. Rectangular chips were used for covalent bonds between nonmetals, while other chips were designed for ionic bonds between metals and nonmetals. This setup also ensured that students couldn't combine 2 metals, since metals don't form chemical bonds with each other to create compounds. In total, we printed 30 atoms for each group, enough for students to experiment with creating various molecules and compounds. To keep everything organized, I labeled the back of each atom with its group number. I also designed a carrying case for storage, with 3 stacks of 10 atoms each, and extra space for bonding chips. For inventory purposes, I listed all the included atoms on the lid of the case. In the future, I'd like to redesign the lid to either slide on or off, or to use hinges, but it still serves its purpose. Once all the materials were ready, it was time for the activity. I prepared a list of molecules and compounds for students to create and divided them into 3 rounds. The molecules increased in complexity through each round as students got more practice. By grouping them into different rounds, students could make the maximum number of substances possible without having to disassemble them until the end of the round. I also had students sketch a few molecules from each round to reinforce their understanding, and showed them different ways that they could draw their models. This strategy allowed for maximum participation between group members. In round 1, students created molecules of nitrogen, oxygen, and hydrogen, demonstrating that some atoms can bond with other atoms of the same element. We also created a few ionic compounds, most notably sodium chloride, and a molecular compound, methane, the simplest hydrocarbon. For round 2, students made several ionic and molecular compounds, including carbon dioxide and ethane, which uses 2 of the 3 carbon atoms. For each round, I had them make an increasingly larger hydrocarbon. In round 3, students made ionic compounds with transition metals like copper, gold, and silver. And finally, they used all of their carbon and hydrogen to make a molecule of propane. If time allows, I include a 4th round where students create larger models like ethanol and nitric acid. These models can't all be made simultaneously, however, because there's not enough atoms in the kit. Next year, I might even have each group collaborate at the end and assemble a large molecule, such as a lipid or a carbohydrate. While this activity works great at the middle school level, there are some serious limitations to these models that you should be made aware of if you plan on using them in your classroom. First, the models only represent single bonds. At the middle school level, we focus on bonding between different types of atoms and don't explore things like double and triple bonds. As such, this approach would not be suitable for a higher level chemistry class, but it works well for introducing my students to the concepts of bonding. Second, the geometry of the molecules is not accurate. For example, iron oxide forms the molecule Fe2O3, which has double bonds and a specific chemical structure. These 2-dimensional models cannot replicate the proper angles of the bonds. To simplify, I represent iron oxide as a single iron and oxygen atom. It's a great oversimplification. And again, this isn't ideal for advanced chemistry, but it works well for building the foundational understanding at the middle school level. Despite these small imperfections, I think this is an effective model for its intended purposes. It was well received by my students, so I'd consider it a success. In the next video, we'll take a look at how my Earth and Space Science class was able to make a 3D printed Hertzsprung-Russell diagram for a chapter on stars and stellar classification. Hope you enjoyed the ride, and don't forget to like and subscribe.